Hello students, my name is Shashank Shekhar. So let us start the exercise of chemical kinetics. First question says, from the rate expression for the following reaction, so we are given some rate expressions. We have to determine the order of the reaction and determine the dimension of the rate constant. So what is the first reaction? Rate expression. So we will write it as rate is equals to K NO raised to the power 2. So two things we have to determine. First of all, the order of reaction. So what will be the order of reaction? It will be 2, because what is order of the reaction? It is basically the summation of powers to which the reactants are raised. So here there is only a single reactant which is raised to a power of 2. Therefore, order will be 2. Now what about the dimension of the rate constant? So let us try to find the dimension of the rate constant. So rate is given as K NO square. So we are interested in finding the unit for this K. For that we know that the rate has a unit of mole per liter. Okay, it is mole per liter per second. That is the concentration consumed per second. And what is the unit of concentration? It's mole per liter. So here concentration has a unit of mole per liter and it is raised to the power 2. So we will square this thing. This would result in, so if we cancel this on both sides, this would result in per second, and in the bottom side we will have, or in the denominator side we will have mole per liter. That would give us per mole liter per second. So this will be the unit of K. Is this clear? So the unit of K will be per mole liter per second. Next question. So for this, what will be the order? Say, so we have two reactants. Each of these are raised to the power 1. So 1 plus 1, that would give you 2 again. So we have calculated the unit of rate constant, or we have determined the unit of rate constant just now. So that would be again mole per mole liter per second for a second order reaction. Next question. First of all, order of the reaction. So it is very clear, we have only one reactant in the rate expression, and that has a power of 3 by 2. Now what about its rate constant concentration, rate constant unit? So again we will write first of all the rate expression that is being given. So it is basically CH3 CHO raised to the power 3 by 2. Now we will put the units here. Rate has a unit of mole per liter per second K, and concentration has a unit of mole per liter 3 by 2. Now if you bring this mole per liter 3 by 2 on this side, it will be mole per liter here, and on the denominator side we will have mole per liter 3 by 2 per second. Now if you bring this upside, that would give us mole per liter 1 minus 3 by 2, or 1 minus 3 by 2, that would be minus, say, minus 1 by 2. So it will be mole per liter minus 1 by 2. Is this clear? So this is the unit. Now if you just multiply this with each of this, so that would give you mole to the power minus 1 by 2, and minus 1 by 2 into minus 1 will give you plus 1 by 2. Okay, and per second. So this will be the unit of your rate constant in case of this equation. So 1 minus 3 by 2, that would give you 2 minus 3 by 2, that is minus 1 by 2. Okay, yeah. So the unit of rate constant is mole inverse half liter plus half per second. Last equation. So according to last equation, the order is 1. Why is it 1? Because we have only one reactant in the rate expression and that has a unit of 1. So that would give you 1. Now, what about the unit? So let us try to determine the unit. So the rate expression is given as rate is equals to K into C2H5Cl. Again, we will write their units, mole per liter per second for rate. For concentration, it is mole per liter. So this and this will be cancelled out and we get the unit of rate constant as per second. Now let us see the solution. So very clear, liter per mole per second. So it is the right way of writing this thing. So instead of writing per mole liter per second, I think you should write liter per mole per second. It is more appropriate. Similarly here also liter per mole per second. Now in case of this it will have, so I have written it in this way, mole minus half, liter plus half and S minus 1. So it is better if you write it in this way. So first the one with the power of positive are written first and then the negative are written on the latter side. For first order we have per second. So this was the first question. Next question says that we have a reaction in which 2 moles of A react with 1 mole of B to give A to B, and the rate expression is given as rate is equals to Ka to the power 1 B to the power 2, and rate constant value is 2.0 into 10 to the power minus 6 mole to the power minus 2 and liter square and per second. Now what we have to calculate? First we have to calculate the initial rate of reaction when A is equals to 0.1 mole inverse and B is equals to 0.2 mole liter inverse. So concentration are given, so here it will be liter. Okay, 0.1 mole per liter inverse and B has a concentration of 0.2 mole per liter inverse. So we have to calculate the rate, initial rate of reaction. So we have this equation and we have the value of concentration. So initial rate is nothing but rate. So if you talk about this rate law expression, so it basically gives you the rate of the reaction at this concentration of A and B. Okay, so we have the concentration, we have K is given as 2 into 10 to the power minus 6. Concentration of A is 0.1 and concentration of B is 0.2 and B has been raised to the power 2. So this is our equation, and after putting the values we get this. Now if you further calculate it, that would give you 2 into 10 to the power minus 6. Okay, that is 2 into this is 10 to the power minus 2 and this is 0.04. Clear? Now further, if you just put off this say decimal, that would give you 10 to the power minus 2 and this is 4 to the 8 and 10 to the power minus 2 if you write it in this way. And after adding the power minus 6, minus 2 and minus 2, that would give you 10 to the power minus 10 mole per liter per second. So this will be the unit of your rate, we know it. So this is the rate. What does the next question says? We have to calculate the rate of reaction after A is reduced to 0.06 mole per liter. So it is basically said here that we have to calculate the rate of reaction after A is being reduced to 0.06. Now we have starting point from 0.1 and we have moved to 0.06. So how many moles of A has been used? So change in concentration of A will be 0.1 minus 0.06. That is 0.04. So 0.04 of mole of A has been mole per liter. This has been consumed. Now 2 moles of A is giving 1 mole of B. So 0.04 will give how many moles of B? So it will take up 0.02 mole. So this much will be consumed because for 1 mole of B, 2 moles of A are consumed. So therefore, for 0.04 mole of A, 0.02 mole of B will be consumed. So if I subtract this 0.2 from 0.02, then I will get the concentration of say B at this point where A has reached to 0.06. So B concentration, so I am writing it B final is equals to 0.2 minus 0.02. That is 10 minus 2, 8, 9 minus 2, 7. 8 to 10, and that is 7 to 9. Right. So this is our final concentration of B, and this is our final concentration of A. So again, if we use the rate law, so this is 2 into 10 to the power minus 6. A is 0.06 and B is 0.78 square. So if you further just calculate this, you will get your rate at this point. So let us see the solution. Same thing has been done. So we got it as 8 into 10 to the power minus 9. So similarly, if A is reduced from 0.1 to 0.06, means 0.04 moles are consumed. Therefore, 0.02 mole of B are consumed. So the available B would be 0.18. Okay, so that was 0.18, not 0.078. So I have subtracted it wrong. Sorry for that. So 0.2 minus 0.08 will give you 0.18. If you put this values here, you will get this at 3.89 mole per liter per second. So here something is missing. So if you just multiply this, so 1860 this, and so power are missing here, so you should do it by yourself. So it should have some 10 to the power minus something. So I think it would be, so basically 18 to the 36, 36 6 ja 6 6 ja 36, right? So we have 3 carry, so it is a square. So this would is giving us 3.89 directly. Okay, so this is giving us 3.89 directly. So 10 to the power minus 6. So if we just 10 to the power minus 2 from here, so 10 to the power minus 8, and 2 times from here, 4 times for here I would say. So minus 4, minus 2, and minus 6. That is minus 12. Next is the decomposition of NH3 on platinum surface is a zero order reaction. So it is given that a decomposition of NH3 is a zero order reaction. What are the rate of production of N2 and H2 if K is given? So we have to calculate the rate of production of N2 and H2 if this is the rate constant. So if you talk about the decomposition of ammonia, so it goes in this way. This is 3, this is 2, and this is our balanced equation. Now what will be the rate of reaction? So rate will be K. So the reactant is NH3 here, and it will be raised to the power 0 because it is a zero order reaction. So that will give us rate is equals to K, and K is already written as 2.5 into 10 to the power minus 4. So that leaves us with the rate of reaction. Okay, this leaves us with the rate of reaction. Now we know that we have seen that that the differential rate law, it written this way, that rate is equals to, what was rate is equals to d of, so basically we have 2 NH3 here. So if we just divide it by 1 by 2, so it will give us 1 by 2 here and 3 by 2 here. Okay, so I'm just say divided this equation by 2, so I got this thing. So rate will be equals to how much? So it will be equals to d of N2 by dt, 1 by 2 divided, okay, with a minus sign because it is for sorry, it will be plus sign because product is there. and this will be 1 by 3 by 2, that is d h2 by dt. That brings us to 2d and 2 by dt is equals to 2 by 3 dh2 by dt. Now we have just found this rate, which is 2.5 into 10 to the power minus 4. If you want to calculate dn2 by dt, that is the rate of production of n2, that will be 2.5 into 10 to the power minus 4 by 2. Similarly, for this it will be, if you want to calculate it for dh2, it will be 3 by 2 multiplied by 2.5 into 10 to the power minus 4. So in this way you can calculate both of this. Let us see the solution. So first we have calculated rate. So rate is nothing but your 2.5 and 10 to the power minus 4. We have just equated this, both of this. So when we equate, we got this dn2 as this much. Okay. And for dh2 we got it as 3 into 10 to the power this. So how is that been solved? Okay. Yeah. Next question. The decomposition of dimethyl ether leads to formation of CH4, H2 and CO. And the reaction rate is given by, rate is equals to KCH3OCH3 raised to the power 3 by 2. Now the rate of reaction is followed by an increase in pressure in a closed vessel. So it is resulting in increase of pressure in a closed vessel. So the rate can also be expressed in terms of partial pressure. That is, rate is equals to P CH3OCH3 raised to the power 3 by 2. If the pressure is measured in bar and time is measured in minutes, then what are the units of rate and rate constant? So what will be the unit of rate first of all? Okay, what will be the unit of rate first of all? That would be bar per minute. Okay, is it clear? It would be bar per minute only. This is for rate. Now how will calculate it for rate constant? So K will be equals to, so rate was bar per minute divided by, so basically here concentration is nothing but your pressure. So I have written in place of concentration bar and our unit is per minute. Now if you bring the CH3 pressure here on this side, that would give you bar to the power 3 by 2. Now if you further calculate it, then it would be 1 minus 3 by 2 and per minute, isn't it? Now 1 minus 3 by 2 would be 1 by 2 per minute. So let us see the solution. It is basically bar to the power minus 1 by 2 minus minute minus 1, it is bar per minute. Clear? Mention the factor that affect the rate of reaction. So what are the factors? So there are 3 factors. First is concentration of reactant. Second is temperature and presence of catalyst. So catalyst basically reduces the activation energy and hence increase the rate of reaction. For temperature, it is dependent whether the reaction is exothermic or endothermic. If it is, so basically the rate of reaction is increased by temperature. But in case of say reversible reaction, the rate of both forward and backward reaction is increased, and now it depends upon the intrinsic property of the reaction, that whether the forward reaction will be increased, rate of forward reaction will be increased more, or whether the rate of backward reaction will be increased more. At last we have concentration. Okay, now this question, a reaction is second order with respect to a reactant. How is the rate of reaction affected if the concentration of the reactant is doubled? So it is written that rate is a second order. So rate of reaction is second order, that brings us to R raised to the power 2. Now what we have done, we have altered the concentration of reaction. So first we have doubled it. 2R. Okay, so that would bring us to, so I'm representing it with, suppose, R dash, so rate dash. So this will be nothing but R square, and I'm bringing this 4 on this side. So we have seen right now that rate is equals to KR square, so I am just replacing this thing with a rate, so that is 4 into rate. So what will happen to rate? Rate will be doubled. Sorry, rate will be increased 4 times. Now for second case, if the concentration is reduced to half, therefore it will become R by 2 square rate dash, or rate dash will be equals to K R square into 1 by 4 is equals to rate. So that would bring us to 1 by 4 times. So it will be say rate will be reduced to 1 by 4 times. Next, so this is the solution. It is 4R and it is 1 by 4th. What is the effect of temperature on the rate of reaction? How can this temperature effect on rate constant be represented quantitatively? So the rate of reaction increases so for each, so it is said that for each degree rise in temperature, for each 10-degree rise in temperature, the reaction is nearly doubled. So it is generalization of the temperature effect, and we have quantitatively found that the rate constant is dependent upon the rate law in this way, rate constant in this way, that is K is equals to A e to the power minus EA by RT, that is our Arrhenius equation, where EA is the activation energy, R is the gas constant, T is the temperature, and A is the pre-exponential factor, right? Or is it sometime it is also told pronounced as exponential factor or Arrhenius factor. So in this way we can quantify the relation of our rate constant with temperature. For question number 8, so we are given a pseudo first order reaction. So basically it is hydrolysis of ester in water, and the following results were obtained. So for different time we have the change in concentration. So at T is equals to 0, we have initially 0.55 mole of ester. Now it is reduced to 0.31, then it is 0.17, then it is 0.085. Now calculate the average rate of reaction between the time interval 30 to 60 seconds. What is the formula for average rate of reaction in terms of say product? So average rate of reaction will be, so between 30 to 60. So this to this. So minus change in concentration of reactant by change in concentration of time. So that would bring us to 0.17 minus 0.31 divided by 60 minus 30. Therefore rate will be equals to, so if you subtract 0.31 minus 0.17, 11 minus 7 4, 2 minus 1 1, so 0.14 by 60 minus 30 30. So this will be our average rate of reaction, 0.14 by 30. You can further evaluate it to get the exact value. Calculate the pseudo first order rate constant for the hydrolysis of water of ester. So we have to calculate K here. What we have to calculate? We have to calculate, so let us see. So we have done it. 0.31 minus this 60 minus 30 is for the first question. For second question, so we know that for a pseudo order reaction, first order reaction, it is a first order reaction, so K will be equals to 2.303 T log R naught minus R. So this is our integrated rate law. So we put all these values here. T is equals to 30, and we can take any concentration, any two concentrations. So we got this as this. So for t 3 times we'll calculate it 2 times. So we got at t is equals to 30 we got 1.911 into 10 to the power minus 2, and for t is equals to 60 we got it as 1.957 into 10 to the power minus 2. So what we do is we calculate it at 3 times. We calculate it for 90 also, and we took the average to calculate the rate constant of the reaction. Question number 9. Our reaction is first order in A and second order in B. So we have to write the differential rate equation. So differential rate equation is rate is equals to K. So what would be the rate? It will be rate is equals to K. So this is the first rate expression, K into A to the power raised to the power. So it is first order with respect to this and second order with respect to this. Okay, clear? So if you write it partially for both of these, then it would be minus dA by dt Ka. Similarly for product B, reactant B, it will be Kb. How is the rate affected on increasing the concentration of B 3 times? So if you increase the concentration of B 3 times, that would increase the rate of reaction by 3 square 9 times. How is the rate affected? If the concentration of both A and B are doubled. So if this is doubled and this is also doubled, that would bring us to 2 to the 4 to the 8. So it will be increased 8 times. Now let us see the solution. So basically they have write it in terms of a reactant commonly. If you want, you can write it in terms of A and B separately also. Now if the concentration of B is increased 3 times, we are getting it 9 times, and if both are doubled, we are getting 8 times. Last question. In a reaction A and B, the initial rate of reaction was measured for differential initial concentration as this. So we have rate at 3 different concentrations. Now what is the order of reaction? So we have to calculate the order of reaction with respect to A and B. So suppose X is the rate of reaction, order of reaction with respect to A, and Y is the order of reaction with respect to B. Now if you write the rate expression for this and this, then it would be rate is equals to, so I'm writing a general statement first of all. So this would be our rate law. So if you consider it for this case, it is 5.07 into 10 to the power minus 5 is equals to, we don't have K value given, A concentration is 0.2 and B concentration is 0.3, X and Y. Similarly, in this case, we have 5.07 into 10 to the power minus 5 K. A concentration is still similar. B concentration is 0.10. That is Y. Now, if I divide both of these equations, then this and this will be 1. This and this will be also 1. That would give us 0.3Y is equals to 1. If you take log on both sides, so that would give you Y. So it is basically, so we have 0.3 and 0.10. So that is nothing but 0.3 by 0.1 raised to the power Y. Okay. So is this clear? So if we are raising something to the power Y and is still getting 1, so this indicates that our Y must be equals to 0. This can be verified with the help of log. If you take log on both sides, that would give you Y log 0.3 by 0.1, and the value of log 1 is 0. That would give you Y is equals to 0. So with respect to B, it is zero order reaction. Now what about with respect to A? So if you calculate it for A, so just put it here, right? Just use this equation. and this equation we have seen it. So let us take this equation and this equation, both of these equations, right? So I will write rate expression for the first one. That would give you 5.07 10 to the power minus 5 is equals to 0.2 raised to the power x. So we have and 0.10 raised to the power y. So we are already found that y is equals to 0. For second, k here. For second, we have 1.43 into 10 to the power minus 4 k and 0.40 raised to the power x, and second is 0.05 raised to the power 0. Now again we divide both of these equations. Now it is already 1. This k and k will cancel out. So it would be basically 5.07 10 to the power minus 5, 1.43 into 10 to the power minus 4, and if you see this, 0.2 by 0.4 raised to the power. So it was 0.2 raised 0.4. Okay. X. Clear? This will be cancelled out. So if you further take log on both sides, that would give you x log. So it is basically 2 by 4. That is 1 by 2 is equals to 5.07 into 10 to the power minus 5 by. So I am taking a log of this 0.4 into 10 to the power minus 4. So if you further evaluate this, you will get your correct answer. Let's see the solution. Okay. So we found y is equals to 0. X you can calculate from here. So you will get this thing as 1. So x will be equals to 1.496. That is approximately 1.5. Therefore, we can write the differential rate equation as minus dr by dt k a to the power 0.5 and b to the power 0. This is our differential rate equation. So with this, I end my lecture. Thank you.